Lehto-26.2.15-20 is nothing short of the awe and humility with which we watch our own selves journeying into space. Today is going to be the story of a billion-kilometer journey that started over 10 years ago and is 25 years in the making, that came to fruition last November as the world and us in Trinidad and Tobago watched CNN and BBC jaw-dropped as a select team of scientists from the European Space Agency, including our speaker this afternoon, Professor Lehto, was part of the historic mission to land the probe the size of a fridge on a piece of a rock, couple kilometers wide, hurtling through space at 65,000 kilometers an hour. I can't even get a dart to throw to a bullseye.
The probe onto the comet and having to travel over 10 years to chase down the comet, traveling at such a fantastic speed, great speed, is to me the most significant scientific achievement of this century.
Dear people, I'm going to tell you about a story of a comet, actually a story of comets, and about some of our recent findings, what we have found about this comet, and also mention briefly what I'm interested in looking for in this comet. Well, one of the most nice relaxing things in the evening is to go out and look at the night sky. It's the same as it was yesterday. You can kind of believe that nothing really changes there. Stars are in the same places, constellations are in the same places. Of course, if you stare long enough from night to night, you're going to see that something moves there. It's easy to notice that the moon moves among the stars. The sun also moves among the stars. And then these brightest stars that are really planets, wanderers, also move among the stars. But besides these things, really nothing else happens there. Of course, the sky rotates as the Earth spins under the stars. But it's really relaxing and confiding to see that the stars are there. Then when something unexpected happens, a star explodes, you get a nova in the sky, or you get a comet in the sky, it spells disaster. This was actually the thought that was still in the 1500s. This is a depiction of the comet 1690. So there's going to be deaths here, and there's going to be wars and plague, and all kind of bad things are going to happen when the comet shows up in the sky. Even Galilei himself thought that the comets are a bad omen. Now, when you see something like this in the sky, your first question is, where is it? Is it close by? Is it far away? A bright comet, you can see that it moves from night to night. Not much, but a little bit. And it's something that most likely you have never seen before. So there was discussion whether comets actually belong to this class of objects. These are upper atmosphere phenomena. These are a few examples that we can see in Finland. In the summertime, I start from this one. This is a summer night. Nights don't get this, any darker than this, and you can see these thin clouds in the sky. These are not ordinary clouds, but noctilucent clouds at a height of 82 kilometers. Then, in the wintertime, you can have bright lights in the sky, and these are called auroras. This was photographed last March. We see them every winter, up in northern Lapland, even pretty much every night, every clear night. Then you can see occasionally beautiful halo displays. So these are all kind of clearly atmospheric things or high atmosphere phenomena. And then there are these funny things that are comets. it was not until about 1550 when Tycho Brahe measured the parallax of the comet. This is like distance by triangulation, and he came to a solution that they must be much more further than the moon. So this put them out of the atmosphere. Many people did not still believe that. But that was a solid measurement, showing that comets are not things in our atmosphere. Comets can look different. Some of them have a narrow tail. This is Ikeya Shan. The stars have a funny appearance here because in this image we have followed the comet. And another comet, Hale-Bopp, this was something like almost 20 years ago, shows two beautiful tails. It shows a dust tail and an ion tail. Usually you see these both. Now, the understanding of the comets was revolutionized in the 1680s when Sir Isaac Newton came up with the theory of gravitation, and Edmund Halley calculated that one of the comets is on an orbit around the sun, and it returns every now and then. This is now known as Halley's Comet, with a period of, I think it was 76 years. It was here the last time in 85, so you can add up. The youngest ones of you are going to see it when it comes back. The older ones may not be around to see them. Okay, so we see a tail. We can calculate the distance of the comet from the orbit, so we can calculate the distance of the tail. It's like hundreds of millions of kilometers. They are huge, really long. But now the problem is that we don't know what is sitting there right in the tip here. What is the nucleus like? What is the body that produces this huge, beautiful thing in the sky? The answer to that came when the expedition was launched to Comet Halley. There were actually 11 different satellites that went to check what Comet Halley looks like, and here's one of the pictures taken by the NASA satellites. It was Giotto satellite. And it showed a body which was about 10 kilometers long and has jets coming out. These are the ones that are going to form the tail. Since then, there have been several other missions to look at other comets, Wild 2, 9P Temple, and 19P Bobby. They also objects kilometers in size. This is a smaller one, about 1.5 kilometers. So we have an idea what the comets look like. They are small bodies, less than 10 kilometers, at least the ones we have visited, and they all look a little bit different. So none of these comets is really like a copy of another one. From Wild 2, I think Wild 2, we got some samples back, but they were with an aerogel, and we're going to show you something much better than those return samples. Okay, so from those missions it became clear what comets are like, sort of. The missions were satellites flying at the speed of several tens of kilometers a second, so very far, very quick. So all the way across Trinidad in 1 second, and the comet was at a distance of about 1,000 kilometers. Some of them a little bit closer, some a little bit further. You can get a picture of the comet, but you cannot really get much information out of it. So the consensus was still built that the comets look something like a Finnish roadside in the spring. This is about now or March that some of the parking lot areas would look like. There's mostly ice and snow, and then there's different kind of dirt, and there's maybe some organic stuff. It makes a minority. So this is like an earthly image of a comet. And now this is kind of the theory that we start building on. So with lots of ice, it makes the comets kind of light. smaller density than water, and then there's this other mineral stuff and maybe organics. These are going to be very important. Now, if we go back in time, in the case of our solar system, we go back about 4.567 billion years. It's actually known quite accurately what's the age of our solar system. The solar system, all the planets, all the comets and all the asteroids were formed about the same time, only within a few million years. And they were formed inside a giant molecular cloud. This picture shows you the giant molecular cloud of Orion, known as M42. It's almost straight overhead in the evening, and you can see it with the binoculars. With binoculars, it looks greenish. With a small telescope, with a big telescope, you get different colors out. Inside this kind of a nebula, there are stars forming, stars with their planets and all the other stuff that comes with that. And this is kind of a place where our solar system was born about 4.5 billion years ago. How do we know it? Because we see planetary systems and stars in formation. This is a planetary, or this is actually not yet a planetary system, but it's one in formation, H Centauri. A star is in the center. This is an infrared image taken with the ESO telescope called ALMA. The star is right here in the center. It has not been ignited yet, so it's kind of doesn't shine brightly. And you see this kind of circular structure here, kind of rings, and then you see these black regions in between. This is a flat system, so it's like a disk. These are called accretion disks or protoplanetary disks, where the star forms in the center, and these darker bands are places where the planets are forming right now. And when they are forming, they are collecting all the material around. So with time, these bands are growing wider, and this dust is going to be collected into the planets. Finally, when the star turns on, it blows out the extra dust. So this is similar to what happened in our solar system about 4.567 billion years ago. Easier number to remember. And this is the time where the comets are from. So they're really old objects in our solar system. They have not changed much. This is kind of one of the important things in the comet studies. This is not a real photograph, but it shows what happens around a star called Beta Pictoris. Beta Pictoris is visible with naked eye. It's on the southern hemisphere, visible from Trinidad in the constellation of Pictoris. There you have the central star, and you see the accretion disk. Here, this is an area where planets are forming at this very moment. And then Beta Pictoris has been shown from observations in infrared that there's at least two populations of comets around this star, close to the accretion disk, and these are apparently quite large comets. So it would be nice to make a small space travel to this Beta Pictoris. It will take a little bit too long, but just in mind, and see these big comets forming. Our solar system may have looked the same in the early phases of its formation. But it's kind of important to note that some of the comets we see today are from this era. Actually, most of the comets are from this era. So they're really ancient. Comets are sometimes really beautiful. This comet McNaught, a couple of years ago, was on an orbit such that it had not been in our solar system previously. So it was a first visit to our solar system, or maybe it was kicked by a star from the outer Oort cloud into a solar system. Just last week, there was news that a star has been identified in the sky that passed the sun from a short distance of only 1 light year. So this happened about 70,000 years ago. It's possible that this comet Mac-Nord was kicked by the gravitational field of that star. But these kind of newcomer comets usually are quite impressive. And Trinidad is a good place to see these because you're close to the equator. So keep on watching the news. These are always mentioned in the news when these come. And let's see if you can see, but the tail of this comet continues all the way to the end here. And this was kind of funny when this Mac-Nord was in the sky. I was thinking that should I fly to South Africa or somewhere in the southern hemisphere just to see this? But I went to the Canary Islands and I took a picture of the western sky after sunset, and I could see these funny kind of wisps in the horizon. It took me a while to realize that I photographed actually the tail of the comet, but the comet itself was below the horizon. That was kind of an interesting experience. So, comets from the previous space flights. Like this, I've shown this before to you, the same picture. They were made at a high speed. So just think that you'd be flying with an airplane and trying to get pictures, for example, airplane flying over Trinidad over the airport, trying to get pictures of the Icacos Peninsula and trying to understand what the trees are there. So this was kind of similar to the flights that happened here, except that the speeds were much higher and the distance was 1,000 kilometers. Things have changed. Things changed drastically with the ESA Rosetta mission. We're talking about a totally different world. Here's an artist's impression of the Rosetta mission. This is the main orbiter, this is the lander, and this is a picture of the comet that the artist had in mind. This was before the encounter. So this is not a real comet, but an artist's impression based on those previous images we have seen. This is the main body of the mission, and it still is. It's kind of the big part of it, and this lander is a small thing. But the lander is quite interesting because it made a good landing on the planet. I'll explain later why it was a good one. Now, in this kind of a big project, you have to have many groups working together. Here we have the European Space Agency, ESA is kind of a lead group. And then there are many collaborations for each instrument. There's a collaboration team. This is a team from Cosimo. And you can see that we have in different institutes in our collaboration. There are kind of two reasons. First of all, the knot is relatively south on the northern hemisphere. It's in the Canary Islands. And with the knot, you can look at sources, comets, objects that are down to 6 degrees from the horizon. Most other telescopes have a hard 15-degree limit. So we can use this to our advantage, and we know we can do that because we just did it last November before the comet went into the glare of the sun. Now there's going to be a gap here before we can observe and before it's visible in Trinidad. I cannot tell you the exact day when it's going to be visible here, but it's going to be sometime in April, maybe first days of May. It can be observed here with the telescope on the physics department roof. And we'll try to do that and get the missing points that no other telescope in the world can do. So UV will be a strong thing there. And I hope these observations are going to be successful. Because at that time the comet is bright. The comet is expected to be the brightest, and it's also closest to the sun. So this is a picture of the ESO telescopes. These are like 8-meter class telescopes. They're big. So one of these buildings, the base of this building is bigger than this auditorium, and you can see that it has 4 stories. The primary mirror in these is 8 meters, so it would be a good part of the width of the room. So mega-sized telescopes, and they have been monitoring the comet until now. And NOT is taking over, and we're trying to get other Canary Island telescopes also. Here's a picture of the NOT. This is in a snowstorm in 2005. The NOT was closed for about 3 days when there was a thick ice cover on the NOT, but when we were observing, it's of course clear and the sky is above us and blue or black. So this has a 2.5-meter telescope inside. This kind of a storm is quite exceptional. It's at a height of 2.5 kilometers, and it does snow every winter, but not this hard. This comet idea by ESO was that we'll send a comet called Virtanen. Virtanen would have been nice because the name would have been a Finnish name. So it would have brought up Finland in a different way on the world map, although Virtanen, it was named by an American which was of Finnish descendant. But then the launch window closed because of weather, and a new comet was selected, 67P, Churyumov-Gerasimenko. With 2 Russian names. Gerasimenko is actually a Ukrainian lady astronomer, and Churyumov is a Russian, and they were observing at Mount Altai. They were looking for Comet Sola. Comet Sola is now visible also in the sky. And they took these frames, and then they found a comet that was a new comet. It was in the wrong position, not fitting the Sola. And the problem at the observatory in the Altai mountain was that there was no way to send a telex to inform the rest of the world about this new comet. So they had to walk down the mountain and send a telex about this comet. It took like two days to get the information to the world. This is now the Rosetta mission satellite on the launch pad. It was launched in March 2004 on its way to the comet. It has been a long trip, and these images show basically the solar system from the top. So the sun is in the center in all of these. These are different episodes of the mission. Earth's orbit is here. Mars's orbit is this one. And then there are 2 other minor body orbits, and this is the comet's orbit, this is Jupiter's orbit. And the space probe's orbit starts from the Earth, and then it goes along this complicated orbit here. And reason why it has this kind of funny bends is that it uses Earth and Mars as a gravitational slingshot to change the orbit. And then it slowly approaches the comet. So in May, it starts to approach the comet, and actual rendezvous is in August. And from August on, it's going to follow the comet on its way around the closest point to the Sun, which is still beyond Earth's orbit, up to December 15, and possibly even now later. We'll see if we can get additional funding. So this is now unique in the sense that we can follow the comet's life from far away in the solar system to the perihelion. We can see how it becomes alive as it approaches the Sun. And And then, okay, here's another picture from the side. You can see that the orbits are tilted. So doing all these maneuvers is not a trivial thing, because you have to calculate that every gram of fuel you're taking abroad, because taking anything up into space is expensive. Then close to a comet, this is approximately to the size. You're still going to make some small changes in the command has been sent, and then you have to wait what happens. Okay, this is again the artist's rendering of the comet, and the Rosetta mission. Now it's hard to get a scale of how big this is. This probe here. It looks like that one. Image may come a little bit later. Okay, so we have two parts in it. We have the orbiter and the lander. If we look at the components now of the orbiter, you can see there are like about a dozen instruments. There are instruments that measure the and there are instruments that measure the plasma field around it, that make sounding measurements with microwaves into the comet, trying to figure out what the interiors of the comet are like. And there are also cameras, so that we can get, first of all, pretty pictures, but we can try to understand the science also of the formations on the comet, search for minerals using ultraviolet light, and so on. Okay, this is now a picture of the orbiter. You can see here is in scale. This is in Göttingen in Germany. These are the solar panels. They're like 4 by 4 meters, and this is the Rosetta instrument. The orbiter is on the other side, whereas this Rosetta instrument is about 3.5 meters by 3.5 by 3.5 cube. The orbiter is actually quite small. It's about, the lander is quite small. It's about this size. So it's like a cubic meter, maybe a little bit more. It makes really nice kind of fresh stuff to have this orbiter, the lander go on the comet, but lots of science is done also in the orbiter. The instruments on the Rosetta, the orbiter and on the lander, so both have a large number of instruments, and the one that I'm involved in is the COSIMO, Cometary Secondary Ion Mass Analyzer. Okay, this is the most distant selfie that has been made. The distance is about 500 million kilometers. So it's the orbiter took a picture of itself and also the comet in the background. Okay, this is what the comet looks like. 67P CG. If you want to shorten that name, of course, you can mention the full name. So it seems like it's made of two parts. This has been described as a duck. So this is the head of the duck, and this is the body of the duck, and this part is the neck. So that's kind of the names that have been used for this. You can see immediately that it's not a smooth object. If you take this and put it here, right here, the head would be on Mount St. Benedict, and the tail of the duck would be just south of the highway. That's about how big it is. So it's 4 kilometers. And then in vertical direction it would be 2 times higher than the northern range. And in the surface on the ground it would just cover St. Augustine. not go to Kulepe or Tunapuna. So it would be about the right size for this place. The density of the comet is quite interesting because it is low. It is about the density of a cork, so it would float on the Atlantic Ocean. It's 0.4 grams per cubic centimeter, so 0.4 times water's density. And now the question that comes out of that is what the comet is inside. Is it like 60% emptiness and only like 40% water or heavier things? Well, I'll come back to that question and see if we can find an answer. Now, the images that have come out from the comet have been just amazing. I mean, the comet is 500 million kilometers from us, the same distance about from the sun, and you can see small rocks. The smallest ones on this image are about 2 meters in size. So this is about the size of this lecture room. You can see smooth areas, and you can see rough areas. You can see areas where there seems to be kind of landslides. Now this kind of object, the direction of down and up is not trivial. On the Earth, when you have a landslide, it always comes down. But what happens here? Well, it's a feeble, faint gravity of the comet that pulls things still kind of down. But on some of these images, the down may be kind of upslope. You have to be careful when you're talking about a small object like this. The gravity is so small that you can jump off the comet. Escape velocity is 1 meter a second. So you can really jump out. So if you're an astronaut there, you have to be really careful. And this is one of the reasons why the Philae lander, the scientists are really careful in doing any moves because they could just kick it out of the comet. Now, the surface has interesting looking features. Of course, many of these get some non-scientists kind of excited what these could be. These kind of funny circular holes, looks like craters that have spilled over, or this kind of table kind of structures. These could be, for example, places where jets have come out from the ground, so kind of bottoms of geysers. There is going to be a lot to study in these images, and the last words have not been said yet. Remember, this is all quite new. And the way we work with this kind of data, I mean, the images are usually released quite quickly, but when we get data from the satellite, first we analyze it, and then we think, then we discuss, then we think again, and then we start thinking, where can we publish it? And once it's published, then we can talk about it. So there are many secrets here that I cannot tell you about, that I know about the comet at this point. I can tell you they're so exciting. But you'll have to read them later from something like Science or Nature. But this picture, I mean, everything I show here has been published or is open. So you can see here like landslides, like something like this. Imagining on the Earth could be hard to see big rocks sitting on a slope. But remember here the gravity is pulling things in. And the direction, this image can change with this in direction. You can see smooth areas with sand dunes on them. So a small object, I mean small comet, 4 kilometers, and a lot of variety on the surface. One of the puzzling things that has been detected is a small crack. This is in the neck region. And it runs all around the neck. It's not quite understood what that is. That's a few meters deep, but that's relatively big for that comet. Maybe this comet is breaking into two. It belongs to the Jupiter family comet, as does a comet called 16P Holmes, and 16P Holmes had a couple of years ago a super outburst. Something brought out of the comet. So it's quite possible that we're also going to see something like a super outburst in this comet when it breaks up. It may break up on this, it could break up on this orbit or in 1,000 years or 10,000 years. We can predict that. But that's an interesting feature. It's also possible that this comet has been a single body and it has eroded from the center. The history of the comet is not really known. It's right now a Jupiter family comet. It was captured by Jupiter maybe 2,000 years ago, and it had a really close byfly of Jupiter, and the orbit prior to that is not known. I mean, it was so close. And maybe that could form these kind of cracks even on a pristine comet. Now, let's look at a little bit about this lander, Philae. There were several, okay, this is now the duck, so that this is the head of the duck. And this was chosen as the landing site. I think it was called landing site S. So this was the main reason for taking all these pretty pictures of the comet as quickly as possible so we could select a landing site. And this cross shows the position. It was carefully selected, that it was relatively smooth, didn't have too deep sand, whatever the sand is, and we could see it. So there's another picture, a blown up picture showing the comet, the Philae's landing site. But then the launch from the orbit was good. Here you can see the Philae coming down, images of the lander, and it made a touchdown point exactly where it was supposed to be, within a couple of meters. So that was successful. Then you can see the three marks here taken on a picture at 5043, and a little bit earlier taking pictures, they're not visible there. So that was a touchdown point. Now the problem was, it was twofold. First of all, there was a harpoon on the Philae, and it should have shot down on the ground and anchored the lander. That didn't work. And the other problem was that the surface was totally different from what we expected. There was a dust layer of maybe about this thick, and under that it was solid hard, really hard. So what you do when you come at a slow speed of less than a meter a second, you bounce at that hard thing and then you fly again. And this lander made a huge jump. You can see it here disappearing from the edge of the image, and then it made another small bounce, third time, and it was lost. We got communication to the lander, and all the science, important science measurements were done. So in that sense, we are safe. But we'd like to do, the Rosetta team would like to do more measurements, but we know this is a panoramic image, the last image that was obtained from the lander. We know that it's somewhere there, sitting in a funny position. Well, the feet should be all on the ground, but it's kind of tilted. And there's a kind of a computer image based on this panorama image. One camera is looking at the jet. So it's somewhere between rocks and tilted. And now we're trying to find it and hope that we're going to contact with it in April or May, when the sun starts to shine into that direction. And then the next thing is to kind of ponder how to deal with the lander. Can we change the position slightly without kicking it out of the comet? Okay, the Rosetta orbiter. Same picture I showed you before. The lander is somewhere on the comet, hidden in the dark shadows. This one orbits or is still orbiting the comet and making measurements all the time with all these instruments. All the instruments get data quite often, once a week, maybe 3 times a week. And I'm involved in an instrument called Cosimo. And just to show you how big these teams are, this is just a team of our instrument from 16 research labs or universities. And this is a number of people. Martin Hilgenbach is a PI right now. What kind of also shows the length of this project. The first PI, Hans Kruger, passed away a couple of years ago. Johan Kissel has retired. And Martin Hilgenbach is now the third PI. So it takes really many graduate student lives to complete this kind of a mission. And you can see the list of people is quite big here, and the red and the orange ones are from Finland, and the red ones are from our university. We have about the workload here when Martin, this was like about a year ago when we were anticipating the approach of the orbiter to the comet. Martin said that now all holidays, summer, winter, Christmas, all holidays are cancelled for at least 2 years. Everything. And he meant that. Because there's so much data coming in. It is nice data, but interpretation is sometimes difficult. So it's full work. We have a meeting in one of the European collaboration partners every month. And then we have every Tuesday and every Friday we have 1-2 hour Skype meetings. So it's all the time in contact with other people and working together. We are the first instrument in space studying a comet with a microscope on board. It's not quite this microscope, but a microscope that has a resolution of 40 micrometers. This is what our instrument looks like. It's about 1 meter total length. So we collect dust on target plates. We can store them. And then we can put them in a measuring position or in a camera position. Here we can take the microscopic pictures, and here we make the actual measurement, shooting the target with the indium beam and channeling it through high electric fields in a mass spectrometer. And what we get out then is a time of flight spectrum. We can measure different elements and different molecules, ions, that have been sputtered from the origin target by the indium beam. This is what the thing looks like. So the dust enters from here. It's collected at a low speed of about 1-2 meters a second. So it's almost like walking speed. You collect the dust and you don't break it. And we can see that we have succeeded in that, whereas the previous aerogel experiment from Comet-2 was at a high speed, tens of kilometers a second. This is what our collecting plates look like. This is 1 by 1 centimeter. This is a clean plate. This is before any dust was collected, taken in the first days of August. And here are some of our first dust particles. So you can see 17th August, nothing, and 24th of August, the first dust particle. There are also some other ones here that turn out to be dust too. So we compare it with the previous plate and see what dust have accumulated. And then we can select one of these and shoot it with an indium beam. And what we get out is a spectrum. It starts really from 0 mass, and it goes all the way to 3,000 mass. So this is just a small part. showing a sodium line and a magnesium line. So these are two minerals that we find there. The amount of sodium is really exceptional. And magnesium comes from some minerals like olivine or pyroxene. And our separation here is quite good. The nominal separation value is mass over delta mass equals 1,600. Here's a picture of a more recent big dust particles. So you can see here the resolution of the microscope, 40 micrometers. This dust particle is 300 micrometers, and this is about 500. This is the same dust particle, but this is illuminated from the right, and this is illuminated from the left. And same thing here from both directions. What this shows is that the cometary dust that we see is extremely fragile. Even at the low speeds that we're collecting, it kind of breaks up partially. And it appears that the density of these dust particles of the porosity is somewhere around 50%. So it's interesting that it is close to the same value as the density, about 0.5, 0.4. So maybe the whole comet has this kind of porosity that goes from the smaller scales to the larger scales. The big questions that we can study in this kind of investigation, of course, the origin of comets is one of the big questions, but it's tied to all of these other things. Water in our oceans, in the Atlantic Ocean, where did it come from? One idea is that it came from asteroids. Another idea is that it was delivered by comets. Both are possible, and this is one of the big questions that's being studied by this comet. It appears now that so far the ratio of heavy hydrogen, deuterium, to normal hydrogen is such that this comet would not explain the values that we see in the oceans. One important question is what kind of organic molecules are found in comets. We know that asteroids have organic molecules. If these comets have organic molecules, they to the Earth, and Earth, could these be the ingredients for the start of life? And what about other quantities in the comets, like amounts of different minerals, and then the structures of the comets, what comets are like inside? These are all kind of important questions. A grand question, what were the conditions during the formation of the solar system? So you see we're going kind of back in time. And my favorite question is, where did the soluble phosphorus come from? So as a short summary, as I said, life is wonderful, life is beautiful, and this is a picture I've shown in many places. But I want to mention now to my dear audience that out of this, in this picture, this is from Trinidad. This is from Trinidad. So I advertise silently Trinidad every time I give a talk in astrobiology. I actually often mention that this is Australia, Denmark, Norway, Denmark, and I think that's also from Denmark, none from Finland. Why is the phosphorus important? Life consists of certain important molecules. This is something we learn in Biology 101, DNA, RNA, and so on. These are the most important that we're interested in. And the important element are SNOPs, CH-NOPS. So you can see here's the phosphorus that I'm searching for. If you look at the DNA molecule, the helix, if you open the helix, phosphorus is sitting there, phosphorus you see in there, it's in the backbone. And now one of the key questions in the formation of during life is, where did this phosphorus come from? Where was the free phosphorus, the phosphorus that was soluble, that could be taken by the molecules that formed the DNA? So, this is what I'm trying to find. I mean, of course, there may be some other serendipitous discoveries also in this study when I'm looking at the different molecules that Cosima has detected. So, now when you go out next time, you don't have to be worried that this one is a comet here. If you know, you can tell that that's a comet. It's slightly yellow and slightly green. All the other things are stars or nebula, and most of these are just stars. But this comet not bringing bad luck to you. Comets are actually good luck, and we're going to see what the next years are going to bring from this Comet 67P. I think it's going to be a really exciting time.
Great pleasure to present you this fascinating. And when I think of what has happened to astronomy over the last 50 years, it's amazing.
Another study person who was instrumental in organizing this event got their shirt in hand.